All right, so we want to use the induction to prove this inequality. We already have your left-hand side as a summation from starting from y equals to 1 all the way up to n. So does anyone want to start with how are we going to use induction to prove this one? Like just for the setup.
I mean, I can do that.
Go ahead.
So first off, we have to set a preposition we're going to prove. How do we say that word? And that's P of n is A of n is less than or equal to B of n, where A of n is equal to the left-hand side and B of n is equal to the right-hand side.
Okay.
And then you prove the base case and
Are you saying A of n and P of n?
I was saying B of n, like ABC.
Yep, and all we need to do is to prove that A of n is less than or equal to B of n for all integer n is greater or equal to 1. Okay. And what is our base case in this case?
Well, A of 1 equals summation from I to 1 to 1 of 1 over 1, which equals 1.
Yep, exactly. Just substitute n equals 1.
Yeah. And then the other one is 2 minus 1 over 1, which is also 1. So the base case is good. And then I would say the induction hypothesis is that A of n minus 1 is less than or equal to B of n minus 1.
Okay, so we assume that P of n is true, and then we want to prove that P of n plus 1 is also true in the inductive steps. If I'm just writing this out, let me take a look at it. So right here, we have assumed this, and how are we going to start our inductive steps?
I'd probably start with A of n and A of n plus 1 and get into a form where there's A of n existent. So like start with the A of n plus 1 equals summation from 1 I equals 1 to n plus 1 1 over I squared, and then factor out the plus 1th term there and make it so it's summation from 1 to n I over 1 squared plus 1 over n plus 1 squared.
Yep, yes, exactly. That's exactly what we're going to do. So we want to start with A sub n plus 1. And that's just by the definition would be the summation from I equals to 1 all the way up to n plus 1. And then we can just, like you said, rewrite the summation as we still start from I equals to 1 and all the way up to n this time. But we still have another, like the last term left out, which would be when I equals to n plus 1. And then you can tell, okay, so now this term, it is A sub n. And in the hypothesis, we know that A sub n is less than B sub n. So if we just substitute the b sub n. In fact, I'm just to get it right, less than or equal to this. All right, so now we have, let me just move on to the next page and rewrite this. Okay, and this is equal to, and what are we going to do next to actually show that, to actually have something that looks like b sub n plus 1 on the right hand side? Since we have the a sub n plus 1, and we know that we're gonna, in the end, we're gonna reach something like b sub n plus 1, which in this case is just 2 minus 1 over n plus 1.
Could you just say that that statement right there is greater than or equal to 2 minus 1 over n, which is greater than or equal to 2 minus 1 over n plus 1?
So you're saying this one right here is less than or equal to, oh, okay, so are you saying that this one is greater than or equal to
Yeah.
2 minus 1 over n?
Yeah.
Okay, and what is the next step?
And then say that is greater than or equal to 2 minus 1 over n plus 1.
Yes, but I think the inequality we want is that the a sub n plus 1 is less than or equal to. But in this case, it turns out to be, we don't actually know which one are bigger of these two.
Okay, that makes sense.
Because you have something that a sub n plus 1 is less than, and then you have less than another term, and this term is also greater than this term. So we're not sure about the relationship between these two. We wanted to show that a sub n plus 1 is less than this. So maybe we can think about just do some work with the algebra. We can rewrite this as n plus 1 times n plus 1 on denominator. So and what can you say about this term? Is it less than something?
It's less than 1/n².
Yes, it's less than 1/n². In other words, is should also less than 1/n times n plus 1. And in fact, we actually have that. So we want to create something that with the 1/n plus 1 term. That's why we don't use the 1/n², because otherwise we won't have something like this. So we'll say, okay, so now we can tell that this is less than 1/n times n plus 1. And then you can rewrite this as 1/n minus 1/n plus 1. So these two are equal. All right, and you have these two terms cancel out. And then you have 2 minus 1/n plus 1. And you're done.
I'm really happy this is probably not going to be on the test.
So I guess for the
we asked
go
her
ahead.
this one in class today, and she couldn't explain it. So I was just wondering how to do it. And she said it probably wouldn't be on the test.
You mean this type of problem, or?
Yeah, like where it's like an inequality like this in the induction hypothesis. Unless, she wasn't right, which I don't hope was true.
I think I actually haven't looked at the test yet. So if she said she's not gonna put anything like the inequality and like just give you an inequality and use deduction to prove, then she won't. All right, so any other questions on this problem 6?
Actually, there was one question that's interesting. Why did it become a plus 1/n minus a 1/n plus 1? Where did that minus come from there?
You mean right here?
Yeah, right there. Like, where'd that minus come from?
Sorry, I think it just like get cut off. Like, do you mean like the minus right here, or?
Yeah, that minus right there. Like, I mean, it's a very convenient minus sign, but I don't see how we get a minus from a plus 1/n plus times by n plus 1, if that makes sense.
Yeah, okay. So actually that if you have something like this, it's just equal to 1/n minus 1/n plus 1, and we can just verify that. So it's just equal to n times n plus 1. And then this is equal to 1/. I guess it's just something like you want to remember, like so like a shortcut of the a way of writing this.
Real quick, can you go back to the last slide? I just need to look at the induction hypothesis again.
Yep.
Thank you. Okay, thank you.
Mm-hmm. All right, so yes, we can go over like how to make a skeleton for the proof by induction. So I'll just like say for this class, like in general, if you got a question to say that use induction to prove something, you always have your 4 steps. Like the first thing is gonna be the problem statement. Basically, you just want to restate what the problem is asking you to prove. And in this case, you can have like a shortcut to say that I want to let the left-hand side equals to an, and I want the right-hand side equals to bn. And then all I need to do is to show that an is less than or equal to bn for every n is greater or equal to 1. And that's just your problem statement. And the next thing is your base case. So the base case is just like whenever someone showed that when n equals 1, the statement holds for n equals 1. You just kind of like basically substitute that n equals 1 into the equation. And for our hypothesis, there's actually several ways to set up the hypothesis. One of them is just pick that the nth term is true, and automatically in the steps, you're just gonna prove that the n plus 1 term is true. And in fact, for the hypothesis and steps, there are actually like many other ways to set up. If you like, you can also set up as like n plus 10 is true in the hypothesis, and then you just prove that n plus 11 is true in the steps. So like what the induction works is that you have your base case proved, and you just want to choose like randomly like one of the term in your sequence, and to show that based on this current term, the next term is always true. That's like the idea of induction.
And then we
Any,
use the base case inside of our induction hypothesis, right? Like we can kind of find examples of the base case inside the induction hypothesis, the induction steps. Is that correct?
So we can found the base case in the. I don't quite.
I understand what he's trying to say. I think if it's okay for me to explain real quick.
Yeah, go ahead.
So what you're trying to say is like we try to find the base case to prove other stuff, right? The only reason we use the base case is to state that the induction hypothesis is true, because like if you look at this example, like if the first one's true, and we can prove that because one is true, the next one is true, then we can say because one is true by the induction, the last step that we do where we prove a of n plus 1 based on a of n. If one is true, then 2 is true. And if 2 is true, 3 is true. So base case just says the first one is true, and that kind of gives us like a starting point to go with for the recursive induction. Does that make sense for you?
Yeah, I think that helps.
Yeah, so yeah, exactly. So the base case kind of gave you like where you want to start, and you have proved like the first one is true. And then whatever you pick like for your hypothesis, like after n equals to 1, if you assume that is true and you just want to prove the next term. All right. Oh, David, you have a question?
Yeah, I also remembered how to do the how we get the 1 minus 1 thing there, like a way to do it generically for all problems. using partial function thing. That basically you do an equation where it's like 1 over n plus 1, n times by n plus 1 equals b over n plus c over n plus 1, and then you solve for b and c. And you just like factor out the very n's on one, like it turns out to be n times b plus c plus b equals 1. And that's just how you do it. I could show it on a slide if you want, but that's simply how it works.
Yeah, so I think that will also work. So there's actually multiple ways to eventually prove. So there's like no restriction on like how you arrive at. Yep. All right. I think I just saw somewhere someone's asking to go over about question 5. So let's just take a look at problem 5. All right, okay, so problem 5 is using the pigeonhole principle to prove that given any 7 integers, there will be 2 that have a sum or difference divisible by 11. All right. Okay, so I guess we can start with just using the hint that what's going to be number of objects in this problem. Oh, okay. Like a basic one. Okay.
Yeah, like a basic proof by induction.
Sure.
Of course, yeah.
Like a basic proof. Let me see if I think we also have problem 4 as proof of induction. Do you want to go over that one or just like a real basic induction proof?
I'm good with whatever. I also didn't mean to interrupt on the pigeonhole one, so we can continue doing that and worry about the other one later.
Yeah, we can. So yeah, sure. Let's just go over the pigeonhole one real quick, and then we can go back to just do like a basic induction proof. All right, and I noticed someone says the number of objects is going to be 7 in this case. All right, and what's going to be the number of objects in a variable container? Or in other words, what's going to be n plus 1?
Since we want to evaluate the sum and the difference between at least 2 of them, then it should be 2.
Yep. All right, and you would get m equals to 1. And just by substitute this m equals 1 into this equation, you will have 1 times n plus 1, that's 7. And you would get n is equal to 6. So we need 6 containers. All right, so and now the thing comes to how are we going to label the 6 containers? So I guess for like this kind of pigeonhole principle problems, the key part is just find out how many containers you have and how are you going to label them. And then everything after that would just be like a typical would just be using the divergence theorem to prove the problem, like by cases. All right, so how are we going to label the 6 containers?
Could you do like the first one is 0, remainder of 0,
Mhm.
and the next 5 would be 1 and 10, and then 2 and 9, and then so on and so forth until the last one is just 11.
Yep. Okay. All right. So now we have our 6 containers labeled. And in this case, we wanted to prove that 2 that have a sum, either have a sum or difference is divisible by 11. So, which that how many cases do you think there will be? Yep, so 2. So what's going to be those 2?
The remainders are the same or they're different.
Yep. So the case 1 would just be let's just say the 2 numbers are A and B, and the first case is going to be A and B have different remainders. Like mode 11. And the case 2 would be A and B have the same remainders, mode 11. All right, so and then everything just after this would be pretty straightforward. So just given as they have the different remainders, we can say that by the divergence theorem, A is equal to, I just use K, 11K1 plus R1. And B is equal to 11K2 plus R2. All right. And what do you know about the R1, R2?
Well, if they're not the same, then they fall into the last 5 boxes, which means that they add to 11.
Yep, right. And this is just the fact that you're going to use in your later proof. So you have R1 plus R2 is equal to 11. Okay, so now you have your case 1 set up. So now in this case, how are you going to start to show that it is divisible by 11? You have your A. and you have your B. And then you know that R1 plus R2 is 11. So what is the next step you're going to do? Are we either going to check the sum or the difference? Well, like since you know that the sum of the remainders is equal to 11, which then you should think that, okay, maybe I can start with the A plus B to show that the sum of these two numbers is divisible by 11. Okay, and you can just substitute this 11 in and take out the 11. And by closure, you can just use some other variables like 11 and all right, and I believe case 2, I want to say that A and B have the same R. Okay, in this case, the only difference is you have the same R for A and B. All right, so since we have the same R, and you're probably thinking we're going to use the difference, because if you're going to use A plus B, the sum, there's actually nothing we know about R plus R what's going to be. So if you just check the difference, A minus B, and we have the R cancel out, and by closure, A minus B is divisible by 11. All right, any other questions on problem 5?
Yeah, so do we have to state that when we rearranged, so I'm worried that we have to state commutativity of addition and associativity of addition when going from these equalities to the final answer.
Yeah, I think it would be better if you just state all the properties you used in the steps.
Okay.
But
Thank you.
yeah. Like for me, I think the most important two properties just like by closure. And right here you want to say that it's by the divergence theorem. All right, so let me just look for a induction problem. I believe we should have some basic reduction proofs in the homework.
Can you do number 9 from the homework?
Homework 2.
The one for proof, yeah.
Yeah, we can do that. Okay. So let's just go over the problem 9 on the homework 2. So let me just write out the questions. So we just want to use the induction to prove that for every integer n is greater or equal to 1, that 5 to the 2n minus 1 is divisible by 3. Okay. So like as always, what you're gonna do is start just the first thing, the problem statement, and that's actually what I just did. It's just gonna be this. All right, and what's going to be the base case? How what is the base case we want to prove?
When it's 1, right?
Yep, when n equals to 1, we want to show that the statement is true. So if you're another way is that you can, in the problem statement, you can say that let your a to the 2n minus 1 equals to an, a sub n. That's easier to use like in the other steps. All right, so for the base case, it's always going to be used, we want to start from n equals 1. No matter how you choose your, no matter where you start your hypothesis and your next steps, the base case will always be when n equals to 1. So now the a1 becomes 5 to the 2 times 1 minus 1. And that's 25 minus 1, and that's 24. Which you know that 24 is divisible by 3. And then you have proved the base case. So let me just rewrite this. Another way to write this, like let's see. And this is by the divergence term. Okay. All right, and which term do you want to start our hypothesis? Usually you want to make sure that you can like choose like the easier term to start, no matter if you're doing this on the quiz or on the homework.
I'd start with n for this problem.
Okay, sure. I'm gonna go with that. So for the hypothesis, we assume that a sub n 5 to the 2n minus 1 equals to 3k. That's our hypothesis. And for the inductive steps, we're gonna show that the next term is also true. All right, so like always, you probably want to start from a sub n plus 1. And just by substitution this to the equation right here, we get 5 to the 2 times n plus 1 and minus 1. If you take out the square, just 2n plus 2. And where do you want to go from here? So, or in other words, what are we trying to show here? What is our goal?
We're trying to get a 5 to the 2n minus 1 so that we can plug in the original assertion, right? The induction hypothesis. And so we take 5 out of, or multiply both sides by 5 or something. We somehow take 25 out of the 5 to the 2n plus 2.
So we can rewrite this as 25 times 5 to 2n. And so we want to somehow take out the 25, like you said. So how, like, we're probably going to somehow construct another 25 over here. So we can actually take out the 25. So how are we going to do that?
Could you subtract 24 from both sides? Or conversely, make it plus 25 minus some other number, or somehow rewrite that 1 into 2 numbers that we need.
Yep. Yeah, exactly. So you have the minus 1 left out, and you want to just trying to take out the 25, where you have 25 times something, which should be your a sub n term. If you just do plus 25 and minus 25, the equation will still keep the same. And what you can do is that, and now this term, this 2 term becomes plus 24 I minus 25. I'm just going to write it right here. So now, if you just take out the 25, and that's 25 times 5 to the 2n minus 1, because you have the minus sign right here. And then plus your 24. All right, and now you can see we have our a sub n. We actually have our exactly same format as a sub n. You can just directly substitute the a sub n, which is 3k. because we know A(n) is divisible by 3. And if you just switch this, and we know that 24 is divisible by 3 as well. So we take out the 3, and that's 8, and that's equal to, by closure, you could just sum like 3n. And thus you're done with the induction proof. All right, any particular question on how we get here?
Could we maybe go over like how to label some of the steps that we did? Like, what would we call the step where we added 25 and subtracted 25?
Did she said about in the class that she wanted every step to be labeled?
I kind of got that impression. Maybe if someone else didn't, they can say something, but
Yeah, she said we have to label associative, commutative, and distributive closure, the properties we're using closure for. But yeah, explicitly associative and commutative every time we use that.
Yeah, so whenever you're using like associative or commutative, you can just list that. Otherwise, I guess for this step, you can call it I'm not sure actually. Let me see.
If we just do substitution, because to get -1, that's equal to 24 plus -25. And that's just a substitution.
Yeah, you could write that. Actually, I don't. So except like all the properties she wanted you guys to list, other than that, I don't think it's necessary to list all the steps like with some property. We're not gonna go over into that detail to just keep track of like which property you guys list. Yeah, I guess you could use substitution. Yeah, so associative, commutative, closure, and divergence theorem, and also by the definition of even and odds, those are all really common properties. If you use them, you just want to list in your problem. All right, so I guess we can move on. So are there any other questions you guys want me to over in the practice quiz on the practice quiz?
Just one
Go
more
for number
question
3.
about this problem. Oh, my bad, bro.
Oh no, we can go over yours.
It was just a little quick thing. So, is it okay if we do inline, declarations where, if on the same line where we put the equation 3 times 25k plus 8, we can put like a comma and then say that 25k plus 8 is an integer?
Yeah.
Okay. I didn't know if it was like if we had to declare that earlier or later or something. I don't know.
So the 25k plus 8, we can just rewrite the 25k plus 8 as other integers. That's just by the closure property.
Right. So when we do that, we have to state that we just use the closure property, right?
Yeah.
Okay. Thank you.
Mm-hmm. So David, do you have any other question you want to go over?
Yeah, I was thinking practice problem 3, I think it was. Yeah, 3.
Okay. Let's just take a look at problem 3. All right, so it's another well, no. Okay, so this one is using an indirect proof by contradiction to show that for integers a and b, if b plus a plus 4 equals to 3b plus 5, then a is not equal to 2b. All right. So if you have a problem asking you to use proof by contradiction or proof by contrapositive, the first thing you're going to do is write out the contradict statement, or like write out the contrapositive statement of the original one. So, and right here we actually have the implication where you have the P implies Q thing. And the P in this case would just be the B plus A plus 4 equals to 3B plus 5. And our Q just A is not equal to 2B. So if we have something like P implies Q, what's going to be the contradiction? How are you going to negate this?
The contradiction would be that A equals 2B. And so we try to prove a case where A equals 2B, right?
Yep. But so like how would you if you give me a problem like this, like P implies Q, how would you write the negation of this?
Oh, P and not Q.
Yep. So P and not Q. So and that becomes like the problem you are actually proving is that A plus B plus 4 equals to 3B. So if A plus B plus 4 equals to 3B plus 5, then A equals to 2B. Or sorry, no, it should be N. Yeah, because it's P and not Q.
Yeah, and then I just rewrite the left equation in terms of A.
Okay.
And then use associative to simplify it, or commutative, or whichever.
So you would get something like 2B plus 1.
Yeah, and then you can either say 0 can equal 1 by combining the two equations, or even can't be odd by division theorem. But I'm just wondering how to phrase it at this point. Like, how do you say at the end, like, woohoo, the contradiction? Like, what's the mathematical way to say that other than eureka?
Yeah, so like this two equation kind of like as you're given this two equation, and then you just start from A, like where you reach the point that A is equal to 2B plus 1, and then just you can say by substitution that the left-hand side is equal to just 2B equals to 2B plus 1. I think you can just keep like writing this, and if you just subtract 2B on both sides, that is 0 equals to 1. And clearly this is a contradiction. you can then say, okay, the statement 0 equals to 1 is a contradiction, and therefore there's no counterexamples, and the original statement must be true.
Cool. So you just say there's no counterexamples because this contradiction exists, and therefore the original. Okay. Awesome.
Yep.
There's that part as well. I was wondering how to do in fancy lingo.
Yeah, I guess you just need to add like a sentence to say that. Okay, so this is contradiction, and yeah, there's no counterexamples.
Awesome. Thanks.
Thank you.
What would you have to say for problem 9, like as a conclusion?
Problem 9. Oh, like on the homework.
Yeah, the one we just did.
So let me. So for problem 9, you would just say, if you get to the point that to show that a sub n plus 1 equals to 3k, and then you can say, by induction, it has been shown that a sub n holds true for integers n is greater or equal to 1.
Thank you.
All right, so this is just gonna be our end of the today review session. So let me just stop the stream right here.